Good afternoon. Let's get started. We're still on the topic of stress with a little more detail today, not generic stress, but let's see how stresses show up in various parts with various loadings. I showed you the simplest possible one yesterday. It's here again. I have a bar in tension. Could also be in compression if I turned the loads around. And I'd have the same formula, P over A, for the stress. And as I said yesterday or the day before, whenever it was, this is the simplest arrangement, and it's one of the few that has uniform stress distribution across the cross-section. Here I show you also the equation for deflection. Delta S is change in length. So that's the deflection or the stretch that results from putting a load P on the beam. And L is the length of the, I should not have said beam there, this is a tension member, the length of the part. So L is its length, A is the cross-sectional area, same as you use for the stress calculation, and E is the Young's modulus of elasticity for the material, which essentially is a material strength property. Actually, it's a material stiffness property, to say it properly. It's not strength, it's stiffness. A material property. So we have geometry in the form of L and A, we have force in the form of P, and we have material property in the form of E, and that's typical for any deflection equation. You must have those three types of things. Okay, here we have a different sort of loading, which is also very common in machinery. It's called direct shear. And you may know that a cutting instrument is called a shear. And the upper left-hand picture there actually depicts what is a shear. You will find one in a machine shop. If you want to cut a piece of steel, you take it to the shear, you put the steel in under the blade, and you step on a pedal, and a blade comes down and goes whack right through the steel like a big scissors. And it's angled like a scissors too. And so this represents that sharp blade, and the steel is being held firmly in something or other here. And there's no gap between the blade and the holder, so I'm right up against the holder, so I don't put any bending on it, and I just rip that material right apart in shear. And that stress associated with that now is a shear stress, tau xy. The load P I'm applying to the shear knife divided by the shear area. Now the shear area might be different under different circumstances, but in general it's the total cross-sectional area. And that's something of a fudge, because as you can visualize, as the blade starts in, there's only a little bit of area getting cut, right? And then a little bit more, a little bit more, a little bit more. When I finally get all the way through, I've cut the whole area. So this is a very crude approximation, because if I looked at the instantaneous shear stresses as it goes through, I would see some sort of a shaped curve that wouldn't be a constant value. So I'm averaging everything here. And the argument there as to why that's legitimate and useful is that in respect to failure, until I've gotten all the way through, I don't really have a failure. So I have to disrupt the entire cross-sectional area before it breaks in two, right? Another form of application of direct shear, which is quite common, is when I have a couple of links together with a pin. And there's supposed to be really no gap in there. I do show a little gap more to emphasize the fact that those are two different pieces. But the ideal situation here, if I were designing this, would be to have minimum gap between those two parts, so I don't put bending on the pin. I'd like it to be in direct shear only. Now that's not truly achievable, because I'm always going to have some clearance, and therefore I'm going to have some bending too. But we're making simplifying assumptions here. So if I say, well, I have zero clearance between the two, I have a direct shear case, same formula, P over the area of the shear, which would be the area of the pin. Now, better arrangement for a whole bunch of reasons is to put this arrangement, this is the same pair of links, but now it's in double shear because I've made one of these links have what's called a clevis, and so or sometimes called a yoke, and I'm reaching around the link, and now I'm supporting the pin on both sides. And the big advantage of this is that now I have these forces in line with one another, whereas over here, they're only really in line if I have zero gap, right? And if, in fact, the average force ends up being out here, and even there I have a bending moment. Here I've canceled the bending moment because the two forces are in line. So that's better in that respect. And I also have twice the shear area now for the same size pin, right? So it's P over 2A. Still pin and hole, there's other ways I can fail this, one of which is called bearing failure, the other is called tear out, and the names are pretty self-describing. Any pin in a hole is a device called a bearing. You know, it's supposed to turn. And it's possible, if I overload it, to egg out the hole. In other words, I change the hole from a round hole to an egg-shaped hole. And I crush the material on one side of the hole. And that's a failure. So that's also P over A, but it's something called the bearing area. Now we have to figure out what the bearing area is. Your instincts might tell you at first to think in terms of the circumference of the pin, right? And say, well, I've got half the circumference of the pin impinging upon the other part. But that's not accurate, because if you get around to the sides of that, the vertical portions of the circle, there's no real way I can push down on the other part there, and somewhere in between I'm having some push. So we average it out by saying, let's call it the diameter of the pin times the length of the engagement. Again, it's a simplifying assumption. And we do a lot of that in this business. And we get down to a simple formula. So the area of the bearing is simply length times diameter. Another possibility is that which is called tear out. I show it with a clevis here. And that means I'm going to literally rip this out by the roots. And one or the other, either the clevis or the link, is going to lose the end of the hole. And that's also a shear failure because I have to, in effect, slice out that little chunk on two surfaces. So I've got 2 times some area, and the area of the tear out will now be that area plus that area. But now again we have this issue, how do I measure that area? Do I take it from the center line of the pin to wherever it happens to intersect the radius? Well, I could do that, but that's fairly cumbersome to deal with. And again, at that outside top and bottom portions on the diameter, there's no way, it has no grip on the part to push on it, really, right? So we average it out. We say, let it be the distance from the edge of the pin to the edge of the outside of the part. And we call that the tear out area. And that makes it a simpler calculation. Here's pictures of parts deliberately failed in a test machine in those 2 modes. So on the left you see a couple of examples of bearing failure where it's just crushed the material and smushed it together to make egg-shaped holes. On the other side, it hasn't quite separated yet. It's ductile material, so it's hanging on for dear life as it's being ripped out by the roots here, and I'm pulling that slug right out of the part. Okay? So bearing and tear out are 2 possibilities. You have to check for all of these in your design because you don't know up front what kind of failure you might have. So you have to guarantee against all these sorts of failure. So we do all of these calculations for a given design setup. Bending is one of the most common and also one of the most dangerous because it tends to give you very high stresses. And bending occurs when you have a beam of some sort with transverse loading, which causes a bending moment. We'll talk more about those in a few minutes. And so I have a simple example here. I have here a noodle, swim noodle. You've probably used one of those. And it's made of foam, and it's quite flexible. And I'm going to let that represent a beam. So I have 2 beam supports here. I finally found a use for these books. I'm going to use them to hold up my beam. The books, by the way, make an excellent doorstop as well, but I recommend that you read the books first before you use them for that purpose. You should read them cover to cover, in fact. So on this noodle, you'll notice I've drawn some lines. So I've got some lines running along the noodle like that. They're not very carefully drawn in freehand, but they'll do. And I have some lines that are annulus rings around the noodle here that are supposed to be perpendicular to the center line of the noodle. Okay? So what I'm going to do is place this on the 2 supports representing a beam, and I'm going to load it in the middle with some kind of a force. And I want you to look at the way the beam changes shape. Obviously it's deflecting downward, And you can see that, and you can see the bend in the lines. But notice the ends. This end over here and that end over here are no longer parallel to one another, nor are they vertical. So the ends of that beam are changing angle, and in fact what they're doing is remaining perpendicular to the center line of the beam, which is now curved. The center line of the beam is called the neutral axis, and all of these sections, including these lines that I've drawn here, here, and here, and here, are remaining perpendicular to that neutral axis, or center line of the beam. And that's important to understand because it tells you what's happening to the molecules of the material inside this beam. Ask yourself, is the distance along this surface the same or different than the difference along the bottom surface when it's curved? And the answer, of course, is they're not the same because they are now at different radii. Now the radius is large, and the difference is only the thickness of this beam. But there is a difference. Therefore, the circumference of the top arc is less than that of the bottom arc. And as a result of that difference, the top surface is being put into compression, and the bottom surface is being put into tension. So that represents how the bending stress, so-called, is distributed across this cross-section. And I'll show you a sketch of that in a minute. But the top surface or the bottom surface, depending upon which way I bend this, one surface will be in compression, one will be in tension, and at the neutral axis there will be zero stress. Now this stress is of the type we call normal stress, the ones I demonstrated on the cube pointing outward from the surface. Now let's take a different prop. Put these aside for a moment. I'm not going to need them now. And I have here a stack of paper. It's right out of the print machine. And I'm going to have to hold this because it can't even support its own weight. But I'm going to consider this to be a beam, and I'm going to allow it to bend under its own weight, as you see. And what I want you to notice is the ends of that beam and what they are doing. Notice that they are still essentially parallel to one another, because in this case I don't have a solid piece of material, but I have a stack of sheets, each of which is free to slip on its neighbor. And what's happening in that slippage is shear. So the sheets are shearing one against the other. And since they are free to move, I don't shorten the top one and lengthen the bottom one. They stay the same length, and they compensate by slipping on one another. Now that slipping motion is short-circuited in this case because we have a solid material. And it can't physically slip, but it's trying to. So as a result of that, we have shear stresses being developed inside the beam called transverse shear is the proper name. And these shear stresses are in essence between the layers of paper, which don't exist, I realize, in this beam. But if you imagine this is made of a bunch of layers, and the layers are effectively glued together, they're trying to separate, and in the process of trying to separate longitudinally in that direction, they are developing shear stresses one to the other. Now, go back to my pad of paper for a second. If I take my pad of paper and I allow it to bend, you can picture that any of the sheets in the middle of the stack are rubbing on their neighbors top and bottom. But what is the top sheet rubbing on the top? There's nothing here to rub against, it's just air. And likewise, the sheet on the bottom has nothing but air on its outside. It does have a sheet on the inside, of course, in both cases. That means that I don't have any shear stress on the outside of the stack. So the shear stress is zero at the top and bottom, and it is maximum in the middle, where I have the most sheets rubbing on one another. That's just the opposite of the bending stresses, which, as I mentioned, are maximally compressive on the top in this case, and maximally tensile on the bottom, and they are zero in the middle. So they're just the reverse. The bending stresses are maximum at the top and bottom, and the shear stresses are zero at the top and bottom and maximum in the middle. Okay, let's go back to the slides now. So we have equations to solve for these. The worst case, of course, will be where I have the largest moment. We'll talk about how we find moments in a bit. The worst case for shear will be wherever that's the largest number. Okay, so this depicts the stress state across the cross-section of a beam in bending. As we just observed, the top half is in compression, the bottom half is in tension. And the thing labeled N is called the neutral axis. And that's called neutral because nothing's happening on it. That's the transition between the compression and the tension, right? So there's no bending stress, it's zero, on the neutral axis. And it is positive, or tensile, which we call positive, above that in this case because of, I'm sorry, below it in this case, I'm upside down. The tension's on the bottom here, and the compression's on the top. And I've turned the arrowheads around. You often will see that drawn as a straight line right across with the arrowheads for the compression on the left-hand side of the center line. That's a perfectly good way to express it. The expression for stress across the vertical dimension is the moment m, which is the applied moment load, times the distance y, and that's the distance from the neutral axis out, over I, and I, you should recall from 2502 or elsewhere, is called the area moment of inertia. And that is a cross-sectional geometric property, and it depends upon the shape of the part. If it's a rectangle, as I show it here, BH cubed over 12 is the equation for the area moment of inertia of that particular cross-section, where B is the base width and H is the total height of the beam in the direction of loading. And notice that H is cubed. So if you double the depth of a beam and leave the width the same, you get 8 times the resistance to bending. That's a very handy thing, because I can make the beam a little bit bigger and get a lot more strength, right, because of that third power relationship. The equations for these various cross-sections are in a table in an appendix in the book. And there's many more of them in other books out there. We're usually interested in the maximum value of the stress which occurs at the outer fiber, and that distance to the outer fiber is generally given the term C. So that's just the largest y that you'll encounter. So we hear the expression commonly MC over I for a beam. That's moment times the distance to the outer fiber divided by this cross-sectional property I. The units of I, by the way, are inches to the 4th power, or millimeters to the 4th power, or meters to the 4th power, depending on what system you're working in. So you can see that changing I has a big effect on the resulting stress for a given moment. Now we have sign conventions for all of this stuff, not all of which make an awful lot of sense. They've been, I think, arbitrarily assigned centuries ago, and we don't want to change them because we'd upset everybody. So we go along with the gag. So positive moments defined as the beam holding water. So I bend it in such a way that it becomes concave up, we say that's a positive moment. Whatever moment made it do that is positive. Okay? Bend it down, that's a negative moment. Shear is considered positive if, as I show in that upper diagram, the shear arrow operating on the cut surface makes it want to rotate clockwise. Again, an arbitrary convention. Doesn't really matter. Okay? Here's our transverse shear stress again. So I got to find in my shear diagram where the V is biggest. There's my sign convention again. And here's the formulas. Now the transverse shear stress is distributed differently. Go back to my stack of paper example here. The very top sheet of paper has no one to rub against. Yeah? Likewise the bottom. So there can be no shear on this guy or that guy. So it's zero at the outer fibers. And it's maximum in the middle where you have the collection of all the other things trying to pull it apart. So this one's maximum on the neutral axis and zero at the outsides, just the opposite of the bending stress. That's a good thing because they don't occur in the same place. Their worst cases don't combine. They are either zero or max in one location or the other. Okay? So you generally represent it looking sort of like a parabola. Now the actual shape of that curve will vary depending on the cross-section of the beam. But in most cases we're interested in the largest value, which is going to occur on the neutral axis. So the shape is of less interest in a detailed sense. General formula magnitude of the shear, which is called V, times some factor Q, which we'll define over here, divided by the same I, and B is the width of the section. I define those here in this diagram. So here's a generic cross-section, a beam of any arbitrary shape. The dark yellow is the area above our shear line that we're interested in. So I want to calculate the shear stress in this plane right here. And we're going to calculate that area and call it A prime. The distance up to where I'm at the moment measuring the shear or calculating the shear stress is, I'll call that Y. B is the width across that. In other words, the size of my shear plane. And Y bar is just the location to the centroid of my yellow area in question. Okay, the A prime area as I've noted it. So again, the shear is distributed in some fashion across this shape, and obviously the shape of it geometrically is going to make a big difference in that function, right? Because the Y bar is going to change and the area is going to change and such. But as it happens, we usually have one or another fairly common cross-section in a beam. It's probably rectangular, or it's an I-beam, or it's round. And so these formulas have been calculated for those common shapes, and they're in a table which we can easily access. I don't show the I-beam here, but it's in a table in the book. So if I have a rectangular section, that formula, after you do all that integration stuff, turns out to be 3/2 V over A, total area. And if it happens to be round, it's 4/3 V over A. These are the maximum values at the neutral axis. And if it's a hollow tube, it's approximately 2 times V over A. Not exactly. Depends on the thickness of the walls as to how that would actually come out. But again, in engineering design, we are usually looking for an estimate that gives us the fastest possible answer, because at the front end of the design process, I'm trying to decide, is the road I'm going down going to lead to a cliff, or is it going to lead to a good solution? And if I'm heading for a cliff, I want to know that long before I get near the edge. So the faster I can get clues as to how my direction is taking me, the better. Once I'm satisfied that I'm in a good direction and perhaps in a reasonable place, then I can go back and recalculate using more accurate methods to get a finer result. Okay? But by then I presumably have the time to do that. Let's look at the beam equations. Now here's where I'm going to introduce to you this topic of singularity functions, which I really begin discussing and explaining in Chapter 3. So you need to go back and read Chapter 3, which is in your assigned readings. I'm not lecturing on it except for this little bit right here. There's other good stuff in there like impact and so forth that I'm not going to talk about. So here we have a fairly simple, on the upper left corner, beam. It's simply supported, meaning there's just 2 supports. The little triangle gizmo is symbolically means the beam is essentially on a knife edge there, and the other end it's on a roller. If it gets a warm day and the beam warms up, it's free to stretch and not have any stresses generated in it by reason of the change in length between the supports. That's the purpose of that notation. Okay? So it says the only way I'm constrained is vertically. Beam is L units long. At A units in, a load is sitting. It's a uniform load. We'll call it W pounds per foot or newtons per meter or whatever terms you want to use. And we want to find out first the reactions, R1 and R2, and then we'll find out the moments and the shear and the deflection. Ultimately, we're after the deflection. And that is always a function of some sort, which we'll depict as y being the deflection as a function of x, where x is the distance along the beam, starting at one end is 0 and going to L. To get that equation, we have to work somewhat backwards. If we differentiate the deflection, we get the slope, usually called theta. So that's dy dx. Differentiate that again, we get the moment function. So that's d2y dx2. Differentiate again, shear. d3y dx3. And finally, the loading function, which is where we really have to start the problem, because that's what we know, is the fourth derivative of deflection. So in essence, I've got a four-part integration process or differentiation process, depending which way I'm going, to deal with here. Okay? And that's where the singularity functions come in, because they make this really easy and straightforward to do. They look very mysterious at first, but once you glom on to how they're really working, they're quite simple to use. So we'll give these standard names. Q is always the loading function. Now we're going to integrate our way down through. So V, if we start with Q, we know Q, that's the loads on our beam. We don't know the deflection, we're trying to find that out. So we can't work from the bottom up, got to work from the top down. So I know the Q. I integrate that once to get the V. And of course that brings in a constant integration C1 that has to be then defined. And then I integrate again to get moment. And now I have two constants to evaluate. Now I integrate again to get theta, and so on and so forth, till finally with 4 iterations I get myself down to deflection. And this is what I'm really after. I want to know how much deflection do I get out of that beam when I put this load on it. Quite often you have a deflection limitation as opposed to a strength limitation. In other words, I'm not looking for the beam not to fail. I'm looking for it not to deflect more than X. Okay? And in most cases that will mean it's far from failure if X is small. I should say Y, because we're using Y for up and down. Okay? So I have to somehow manipulate these equations. So what we're going to do that is, well, I guess I haven't got to that slide yet. So here's some other loading conditions. These are in your book for examples. I'll give you an example in Chapter 4 of each of these cases. And I'm going to say in a slide that's coming up pretty soon, go study these examples. The top two are quite common. The bottom two are, well, that one's somewhat uncommon. This one is not uncommon. You often have more than one support. So here I could have a point load like this over here, or I could have some combination of the two, right? I happen to put a distributed load on the simple supported and a point load on the cantilever. But the two most common arrangements are simple support, hold it at either end, or drill a hole in the wall and bury it in the wall and put a load on it out here, like a flagpole. Okay? Cantilever beam versus simple supported beam. And then I can have other variants, like this load is increasing linearly as it goes. I've never encountered one of those in practice. Here, constant loads common. Multiple supports are common. Here are our singularity functions. Quadratically distributed loads, which I don't show a picture of, that would be a parabola here, can be represented by this notation, and I'll explain this as we go. This is x minus a. Now x, of course, is just where I happen to be on the beam. X is my independent variable. I usually start at the left because that's sort of conventional in our system, but you don't have to. You can go from the right to the left, doesn't matter. So say 0 is over here on the left, and over here x becomes L. So it runs from 0 to L. So x minus A is the point at which the load starts, which could be 0 if the load started all the way at the left end, but in general it doesn't have to be, so we put it in as a term. And that's to the second power. Now that looks like just a parenthesis to the power, but it's something else. These brackets denote this being a singularity function, and by that is meant what you see in text right below that. This function, because of the brackets, is 0 when x is less than or equal to a, and it's equal to x minus a squared when x is greater than a. So what's that saying? It says as I start to walk across the beam, until I get to a, there is no load from this guy. It's 0. Okay? Well, that's what the picture looks like. There's nothing there, right? Then I get to A, and I start to pick up load. And it's not that picture, because this is a parabola, so I start picking it up as the square of x. Parabolic distribution. I don't have that shown. I've also never encountered that in my life. But, you know, it's another possible function. So they include it in the list. This is also not very realistic. The unit ramp, that is this picture right here. Same deal. When x is less than or equal to a, there's nothing happening. So it's 0. When it gets to be x minus a, x greater than a, I'm sorry, then it becomes equal to x minus a. Uniformly distributed load can be represented by what's called the unit step function, and that's to the 0th power. So notice that only things changing here is the power. And this is defined as when x is less than a, it's 0, and it's 1 when x is greater than a. And at x equals a, it's undefined. Why is it undefined? Because you're right on that vertical piece right there. And I have multiple values, right? I don't know whether I'm down at the bottom of the thing or at the top or somewhere in between. So we don't even try to define it there. We just hop over that point and go to where it's got some value, right? We skip that. A concentrated force like this guy has a really weird definition, this unit impulse function. It's actually also known as the Dirac delta function. You ever run across that term in a math course? You have. Yeah. And Mr. Dirac was some kind of a genius. He came up with this idea that at first glance looks totally bogus, but it works like a charm. He said a pulse like that, which has 0 width and some height, sometimes called the unit impulse function, sometimes called the Dirac delta function, is 0 when x is less than a, infinity when x equals a, and 0 when x is greater than a. So it goes 0, 0, 0, 0, 0, infinity, 0, 0, 0, 0, 0. Well, we know nothing can really be infinity. But then he goes on to define that as having an integral. Well, which, of course, the definition of the integral, right, is the area under the curve, right? And so we have an area now of something that's infinitely high and 0 wide. So what the heck is 0 times infinity? Dirac says it ain't 0, it's 1. So this is defined as having an area of 1 unit. And that's what makes it work. So it's very useful because we have those loads all over the place, point loads. If we keep differentiating, we go down all the power to minus 2. Defined as 0 when x is less than a, indeterminate when x equals a, and 0 when x equals a. It sounds like it's nothing, but it actually is representing a unit couple. So here I'm putting a moment or a couple on that thing. A couple, of course, being two forces that are equal and opposite, right? And it's worth 1 unit of moment. So much like the Dirac thing is sort of arbitrarily defined, but it works. These have other names. I mentioned Dirac. This is called Mr. Heaviside. Came up with this guy, I think, before Mr. Dirac was around to come up with this guy. But both of these functions are extremely useful in all sorts of mathematics. On to how we use these. So what I'm showing you here, I'm referring to as pseudocode. What does that mean? It means it's written sort of like computer language, but it's not specific to any particular computer language. But every computer language will have if tests in it. That's generic. And that's really all this is. And all have some kind of a loop. And this is a for loop, which is typical in BASIC. So for x equals 0 to L, so it's going to run the values of x from 0 to L. The implication is it steps by 1. It keeps doing that, increasing x by 1 every time it goes through the loop and goes back and does it again until x finally gets to L and it stops. And inside the loop I have, if the absolute value of the difference between x and a is less than some tiny number that I pick, well, I got 4 zeros and 1, that's pretty small, then y of x is going to be equal to some number of magnitude, which I have to define externally. So I've said magnitude is, that's the size of my load. You know, I got a 100-pound load. Magnitude is 100. Well, the integral of this guy is 1, so 1 times 100 is 100. I've got code now that can essentially walk across the entire beam and apply the loads in the right amounts, in the right places, and I can write one set of equations to handle the whole beam if I have these things in it. The step. Same sort of loop, and I say if x is less than a, then y of x is 0. Well, that's the definition of the function. Otherwise, y of x is equal to whatever number I give it. Okay? So now I go from 0, 0, 0, 0 to 20 pounds per inch, all the way to there, and stop. Okay? And so forth. Ramp, same deal, except now it's going up like this. Parabolics going up like this, cubics going up like that. So to express their integrals, we have these expressions, and we're integrating from minus infinity to x in all cases. So that means that we're sort of off the beam at minus infinity, and I'm assuming x goes positive from left end of beam to right. Lambda is just a dummy integration variable standing in for x. So these expressions allow me to work those integrals. So I start by writing the Q equation with the appropriate collection of these things for pulses and uniform things, and then I integrate using these expressions to get the other four equations: v, moment, slope, and y from the Q. There's 5 to start with. So a -1 function, which is an applied point load, integrates to a step. So that means the pulse in my loading diagram becomes a step in my shear diagram, right? And that step in my shear diagram becomes a straight line in the moment diagram, right? So as I said, examples 4.4 through 4.7 do those examples of those 4 flavors of beam completely with no left out steps. And you really need to put your nose into those until you understand what's going on and how to manipulate these funny functions called singularity functions. The actual computation of them is made very simple by coding up that pseudocode that I just showed you. Torsional loading, different animal altogether. Look at the first line. When members are loaded with a moment about a longitudinal axis, they are said to be in torsion, and the applied moment is then called a torque. I see that I have what I was about to say right there in the first sentence. To a physicist, every turning force, which is a force times a distance, is probably called a torque. I hear my physicist lunchmates using this term all the time for anything. And they're technically correct, because force times distance, we're not talking energy here, we're talking work, we're in a different context. That's a turning force, sometimes called, and you could call it either a moment or a torque. It goes by both names, okay? And other than in mechanical engineering, people seem to use them interchangeably. We cannot afford to do that, because the equations for those two cases are so different that we need to differentiate the terms to keep straight what equations we need to solve the problem, okay? So personally, I religiously avoid using the wrong term for the wrong turning force. And the difference is a moment is directed transverse to the long axis. Here's our noodle again, and I'm going to use it this time to point out the difference between what we refer to as a bending moment and a torque. A moment is in a direction transverse to the long axis of the piece in question, and the long axis, so of course, is the center line of this cylinder. And so when I bend it this way, we're going to call that a bending moment. But when I twist it, one end versus the other, we're going to call that a torque. And I want you to observe what's happening to the straight lines along the elements of this cylinder as I twist that in torque. Notice that they are changing angle, and that's indicative of the fact that I have torsional shear stress being developed in this noodle as a result of my torque being applied on the ends. Torque is a twisting force, as is a bending moment, but we call them by different names because their calculation equations are quite different, and it serves as an alert to the mechanical engineer as to which set of equations he needs in either case. So to understand what's happening inside the material, one way to think of it is to imagine this made of a series of slices, perhaps like a piece of bologna with a bunch of bologna slices in it. And let's assume those bologna slices are able to slip on one another as I twist this. And the torque that I'm applying is going to cause those slices to slide on one another, and that's the torsional shear stress, so-called. Now that will be maximal at the outside surface and 0 at the center, and it will be the same magnitude at any given radius all the way around the circumference. So it's like a fan. If I can imagine, or if you can imagine, that this piece of stack of paper here is like a noodle in this direction, and I twist it, because it's going to stay in one position on the table, and I'm going to twist the top sheets. I don't know how well you can see that from your angle. I'll hold it up so you can see it a little bit better. So I've applied what amounts to a torque to that system, and you can see the sheets of paper have slipped on one another. And you can also see that at the center of the rotation, which is in the middle of the rectangle, there has not been any significant slip, which is why the torsional shear is 0 at the center, and it's maximal at the outside. Let's go back to our slides and we can see some other demonstrations of this. So here you see what I just demonstrated. Here it's buried in the wall, so I have essentially a cantilevered shaft, and I'm putting a torque on the end of it. And I'm getting a distribution of stress, tau, which looks much like the bending stress distribution, with one big difference, and that is this is all shear. To picture this being shear, I think you followed my paper example very well for shear in a beam. Yeah? You can see those sheets slipping on one another. Imagine this is not a noodle, but rather a big stack of Necco wafers. You know what Necco wafers are? Are they still around? Yeah. Been around forever, right? They just get into trouble because they changed the color. People didn't buy them. Imagine this is a bunch of Necco wafers, right? And now I grab one end and the other, and I twist the stack of Necco wafers, just holding onto the two end ones. What's happening? They're all sliding on one another, aren't they? That's my torsional shear, okay? Just like this is shear due to bending, that's torsional shear. I can have them both present at the same time. That's nothing against that, okay? So that's what we're talking about. It's shear on vertical planes, and thus this is not plus and minus. That's just shear. And I have the maximum amount at the outer fiber and 0 at the center, and it's all the way around. I show it like it's the top and bottom. It's all the way around. Okay? So the whole outer fiber is getting sheared maximally, and the axis is getting nothing. So we have a set of assumptions here. The element is distant from the applied loads or external constraints. The reason for that is when I grab this thing to twist it, I grab it here and I grab it here. I got to squeeze the dickens out of this in order to be able to do this, right? In the process of squeezing, I'm putting other stresses in there. And that's complicating the situation under my hands. But over here, the effect of my hands is negligible. So this assumption says I'm away from where I'm grabbing it or doing other things to it. Okay? What's the next one? It's being loaded normal to its axis, and I don't have axial bending or direct shear loads present, so it's pure torsion. Cross sections of the bar remain plane and perpendicular, like my Necco wafers. Material is homogeneous, isotropic, and obeys Hooke's law. We're always assuming that in all cases. Stresses remain below the elastic limit, because then I've gone off the straight part of Hooke's curve, right, from your side, and I'm going into nonlinear land, and all bets are off at that point. Bar is initially straight. Here are the equations that are relevant. Circular sections are pretty easy to calculate. The shear stress is T for torque times rho, which is the radius to any point, so it's a general equation, divided by J. And J is the polar moment of inertia, area moment of inertia, which is related to the I. It's similar to the I, but it's differently calculated. And the formulas are for various sections are given to you in the book. And the angular deflection, given the name theta, is T, torque, times length of beam over JG. Now, G is the shear modulus of the material, which is related to Young's modulus E and Poisson's ratio, and can be calculated from those two values. So that's a material property. And the J, I already mentioned the J. What have I not mentioned? I guess that's it. I did T, L, M, G, and J. So you got it all, right? Here's the formula for circular sections J, pi d fourth over 32. Notice the fourth power. A little bit more diameter, you got an awful lot more J, which really stiffens the system up and strengthens it as well, right? Non-circular sections are a different breed of cat altogether. So we have a generalized equation that says the tau max, which would be at the outer fiber, is torque divided by some factor Q. We'll have to look at what Q is in a minute. Theta is TL over kg, and K is another factor, not the same as J. And those are given to you for a few examples in a table here. And again, there are other references that have dozens of these tables for different shapes. To find it for a given arbitrary shape is an integration job, which is a bit tedious and messy. So the simple shapes have been done for you. So you can pull the K's and the Q's out of a table like this, get into the formula, and get your results. So I'm going to go through this. This is an example in Chapter 4, and I think it's a very critical example for you to understand torsion. It really brings the point home, I think. So here I'm going to take the same piece of metal, and I take a piece of metal that's a millimeter thick, 100 millimeters wide, W and T there in the diagram, and it's steel, so it's got a G of 81 gigapascals roughly, and it's got 1 meter of length, so it's this long, this high, and a millimeter thick, okay? And I'm going to grab that. This paper can represent it. It's a flat sheet. And the first thing I'm going to do is I'm going to grab the edges by some magic, and I'm going to twist them. I'm going to calculate for a given torque that I'm going to put on them, how much twist or theta do I get out of this thing, okay? And then the second step, I'm going to take this and I'm going to roll it into a circular shape, like so. But my welder's on the blink, so I'm not going to weld it, I'm going to leave it. And now I'm going to somehow grab the two ends of that, and I'm going to twist again and calculate the deflection, okay? Now my welder gets fixed, and I'm going to take and weld that seam, and that's the one on the lower right, and I'm going to take another piece of steel of the same sort, and I'm going to bend it into a square shape and weld it. So those are my 4 examples, okay? And I'm going to apply the appropriate formulas from that table, which involve the K's and the Q's. K for the, I'm really looking at deflection, so I only need the K. And the K is messy, but you know, that's calculable. A and B are the generalized dimensions of the plate. Here they're T and W. And so I do the calculation, TL over GK, and I get 214 degrees. How much torque am I putting on this, by the way? 10 Newton meters. So 10 newtons at a 1 meter radius, essentially. That's not a very large torque. So I'm taking this millimeter thick piece of steel, and I'm wrapping it up like a pretzel, 214 degrees. Okay, make a propeller blade out of it. So that's my first example. Now, second example is I take a new piece of steel, same size, I roll it in a rolling machine, nice circle, comes together nice, but I don't have my welder working, so I can't weld it. And I grab that by some magic, and I do the same thing, and I get more deflection, 220 degrees almost. Saying the shape doesn't much matter, because any open shape is lousy in torsion. If I took the square one and did the same thing, I didn't bother to do that one, it would be a number like this too, okay? Now I get my welder going, and I take the square one, and I bend that up, and I weld it together. Now I load it, and I get 1/2 of 1 degree. That's dramatic. I went from 214 to a half, factor of 400 plus, by the simple act of making it a closed shape. Okay, and that's the key to torsion resistance. Now I take my circle and weld it, and I'm down to 1/3 of a degree. And that was 220 degrees. So I've gone from 220 to 0.31, which is an order of magnitude 600 or something like that. Enormous. So you never, ever use an open shape in torsion loading. It's stupid. It's crazy. It doesn't work. And that includes, by the way, open shapes include I-beams, C-channels. Any shape that isn't closed is no good in torsion. Don't ever forget that. Okay? So here's my summary. Use a closed section. Circular shape is optimal. So if you have no other constraints against using a circular shape in torsion, that's it. It's the optimal solution. Have you ever seen a non-circular shaft? I don't think so. Okay?